It's a great pleasure to welcome today CHRISTOPH LEHNER from the Max Planck for the History of the Sciences. CHRISTOPH is a historian of physics. He did his PhD at Stanford University, and from there moved on to work on the Einstein papers. He spent time at Boston University and at Caltech to be the senior editor of the Einstein papers. After that time, he came to Berlin, was the one driving the quantum history project on Einstein's centennial anniversary that brought to light many fantastic publications, and we were actively collaborating during that time. I think this was the first entanglement source back then that went on public display out of Anton's lab that emerged out of that.
That was the Einstein exhibit, yeah.
That was the that was the Einstein exhibit with the big public exhibit, the first really working entanglement source in the museum in Berlin, I think. This was the in Berlin, yeah. Sven Ramelow set it up back then, I think. Yeah, exactly. Yeah, right. Yeah, and so CHRISTOPH is really the outspoken history expert when it comes to the topic of entanglement, and we are very happy to hear today about the historic development and connections related to the EPR paper and thoughts. So, CHRISTOPH.
Thank you very much, Markus, and thank you, Markus and Anton, for the invitation. Very happy to be back in Berlin. I was here, I think it was like 5 years ago, to talk like very much about the prehistory of Einstein, Podolsky, Rosen, and what we found in the notebooks of Schrödinger. I'll do that a little bit briefer today again. But I want to talk a little bit more about sort of the bigger picture and sort of about the meta-theoretical thought, I don't want to yet say metaphysical thought, of Einstein and Schrödinger in this whole debate about the interpretation of quantum mechanics, and not so much sort of about just the small-scale history. So this is going to be sort of a rather wide-ranging talk, and I hope I'm not like, way too long, so I'll try and be somewhat quick. So let me start with Albert Einstein and his ideas about realism. One quote from Einstein that you've probably heard is this famous saying, "God doesn't play dice." So let me just start out with saying that this was sort of a joking remark he made in a letter to Max Born, and that was definitely not what lay at the base of his ideas about quantum mechanics. This is sort of a cliche of Einstein as the 19th century physics that cannot leave from his preconceived notions about how the world should work. So let me quote you a letter from Wolfgang Pauli to Max Born, where he sets Max Born straight about this issue. In particular, Einstein, as he expressly repeated to me, does not consider the concept of determinism to be as fundamental as it is often is treated, and strenuously denied that he ever made any such postulate. Rather, Einstein's starting point is realistic, not deterministic. That is, his philosophical prejudice is a different one. So Pauli, of course, still considered this outdated philosophical prejudice, this realism of Einstein, but he saw quite correctly that was the issue that Einstein cared about. So I want to start this a little bit about Einstein's realism and why I think it's not what people usually conceived it to be. It is, as I said, this central issue in his critique of quantum mechanics, or at least the standard interpretation of it. It comes together with, in his later days, a quite outspoken critique of positivism as sort of a philosophical and theory of science attitude. And as such, it was seen as sort of this naive attitude of the scientist that believes in this objective world out there, and that physics is supposed to give you a correct picture of what's out there. Let me again quote you a letter, this time from Einstein to Mr. Herbert Samuel, who is not further known, but that he wrote a book on realism where he defends exactly this sort of classical philosophically realistic attitude. So Einstein writes to Mr. Samuel, "The real isn't given to us in any way immediately. Only the experiences of human beings are given to us. The positing of the real as existing independently of my experience is a totality of intellectual constructs." So this is not at all what we think of realism in the traditional philosophical attitude. Our trust in the belief system about reality rests only on the fact that those concepts and relations that we posit as real stand in a relation of correspondence with our experience. This is the only ground for the truth of our statements. So this is in no way a contradiction to positivism as it's traditionally presented, right? I mean, it's only our experiences that define the truth or correctness of a theory, not that it in any way reflects some objective reality that exists independent of our knowledge. So then what is the realism? Arthur Fine in the 80s made a proposal. He says Einstein theorizes realism, that reality for Einstein is not a concept beyond the theory that the theory is compared to, but that it is a concept within the theory, that it's a category within the theory that plays a role as a theoretical concept. And this, I think, is a very correct observation. Otherwise, I don't agree with what Fine says about Einstein, but I think that is a very important observation. So let me talk a little bit about Einstein's general relativity and how he started after 1915 in defending general relativity, talking about philosophy of science, talking about the method of physics as he saw it, and why relativity was justified by that method. And there's a very interesting exchange with Moritz Schlick when he was not yet in Vienna and not yet sort of great philosophical fame, but when he was still a young professor in Rostock, I think it was, and had just written a book about epistemology, and then wrote a very practically the first book on general relativity that Einstein appreciated very much. You know, this was in the early years when nobody even noticed general relativity, and sort of explained general relativity in more philosophical terms. And one of the important points that Schlick makes is exactly discussing the methodological value of this famous point coincident argument that Einstein makes within general relativity, that two solutions of the equation of motion are only different if they actually have different events within them. If they just consist of moving the whole world, deforming the whole world, then it's not a different solution, right? Seems to us now pretty obvious, but it actually misled Einstein for 2 years into thinking that the original equations of motion were not correct. So one very important lesson in general relativity is only covariant objects have objective value, right? Everything that is coordinate dependent is not objective. So Einstein writes a letter to Schlick within this discussion, where he makes a remark that I find very illuminating about his attitude about reality. He writes to Schlick, "It seems to me that the word real is understood in two different ways, depending on whether it is said about sensations or about events, i.e. matters of fact in the sense of physics. If two peoples meaning cultures, tribes, whatever, not two people, do physics independently of each other, they will create systems that certainly agree with regard to the sensations, right? We all have the same appearances that we start out with. Elements in the sense of Mach, right? That's what Mach thinks we need to build all of our theories out of these elements of our immediate sensual experiences. The intellectual constructs that both think up to connect these elements can differ vastly, right? They can make completely different theories to explain their immediate sensations. Both constructs also need not agree in regard to the events, because they certainly belong among the conceptual constructs. So even what we call a physical event, a basic building block of our theory, does not need to agree among different theories. Real. Yeah.
I assume this was written in German.
Yeah, yeah.
The translation of sensation events is what in that case?
Empfindungen.
Empfindungen und
Ja.
Ereignisse.
Ereignisse, ja. Real in the sense of irrefutably given in experience are only the elements but not the events. However, if we designate as real that what is arranged by us in the schema of space and time, as you have done in your epistemology, so this is pre-positivistic Schlick as a footnote, then without doubt it is mainly the events that are real. What we now designate as real in physics is doubtlessly the spatio-temporally arranged, not the immediately given. The immediately given can be an illusion. Conversely, the spatio-temporally arranged can be a sterile concept that doesn't contribute to the elucidation of the connections between the immediately given. I would propose a neat separation of concepts here. So what Einstein says is we need to separate two senses of reality. One, this reality in the traditional epistemological sense, as that what is immediately given to us, the appearances that we start out with when we build our theories, and on the other hand, a theoretical concept of reality that describes that what the theory designates as objectively being out there. But that we have no immediate access to. This is a theoretical construct. It's not something that we ever experience. It itself is part of the theory. So let me call these for short terms phenomenal reality, right? Our direct perceptions, and objective reality, the theoretical concept of what is out there. So to give you a little example of this, and I think it's a nice example because it's right from the same time, is Einstein's discussion about the reality of the gravitational field within general relativity. You might remember that was the original idea of Einstein that led him to general relativity, is that when you're in free fall, right, then you don't feel the gravitational field. There is no gravitational field for you. So gravitation, the existence of the gravitational field is relative to the state of the observer. Interestingly, however, he maintains in a later I'm sorry, I'm missing a. Thought I had another slide here. Whatever. He constructs an energy of the gravitational field and proposes that in a paper, and immediately gets, of course, the protest, since the gravitational field itself is relative to a state of the observer. Its energy is 2, right? This gravitational field energy is constructed out of the CHRISTOPH symbols, right? That are itself coordinate derivatives of the metric tensor. So it's not a covariant quantity, and insofar cannot be any cannot have an objective reality exactly according to this idea of general covariance. But Einstein responds, yes, that's true. It's not an absolute and objective quantity. However, it is an important quantity for a specific situated observer, just like, for example, the kinetic energy is not independent of the Newtonian or special relativistic coordinate system. However, right, it's still a sensible physical concept, as long as you keep in mind that it is in reference to a specific observer, right? Of course, if you have relativity, kinetic energy always depends on where you judge the velocity from. So again, he distinguishes between the invariant concepts, like for example the Riemann tensor, that has an observer-independent objective reality, right? Like these Ereignisse that he talks about, Tutschlik. And on the other hand, about the coordinate-dependent objects, like the gravitational field and its energy, that have, even though they're not objective, an important phenomenal reality that we can just as well talk about in physics too. Only caveat, of course, is that the fundamental natural laws, right, like the equations of motions, can only be defined on the description-independent objects, right? They better not depend on the position of an observer. And that is what I would call his principle of methodological realism, right? The objective reality is what the physical laws are defined in, but that does not say how the world appears to us, to our direct observations. There's more to that. So one more example in Einstein until I move on, and that is statistical mechanics. As you know, Einstein also did a lot of work, probably most of his work in his life, in statistical mechanics. And one of the first things that he did was the famous explanation of Brownian motion as arising from thermal fluctuations. And as a way to, for one, really prove the reality of atoms, and secondly, actually give numerical value for the Avogadro number, right? The number of atoms in a unit quantity of matter. So with that comes, really early on in Einstein, a view of statistical mechanics that, for example, treats macroscopic quantities as time averages, right? We cannot have any other definition of macroscopic quantities, but as, for example, temperature or pressure or things like that, as sort of the time averages of the microscopic fluctuating quantities that are objectively out there. And again, right, he distinguishes between this objective reality of the microphysics of the moving and bouncing and fluctuating matter of atomistic nature, and the phenomenal reality as it is described in thermodynamics and the macro states in how we see physics from our point of view. So again, right, this is a distinguish between the appearances to us as the physical observer and the objective reality that is in no way directly observable to us, that is all in all a theoretical construct.
Is it necessary for objective reality to be sharply defined?
Einstein would definitely... Einstein would have definitely said yes, right? It has to be a precise physical theory, right? A mathematically determined physical theory that gives you this, you know, otherwise it's just not a good theory, right? Otherwise it's just not a good theory, right? If it's not a clear mathematical expression of you know, laws of nature, then he would, you know, and objective reality is only a concept within that theory, right? So it's always only as good as the theory that it's in. So I would say yes, he would have always insisted, and then we'll get to that in quantum mechanics, right? That he, of course, was not satisfied with.
But then it's a theory-laden concept, because you can never prove that the temperature of a large body is statistically defined experimentally. I mean, you cannot never measure it precise enough to see how it fluctuates.
Yeah. I mean, that's exactly what it says, right? I mean, theories, that's his eternal point, right? Theories are free creations of the human mind, right? Nothing in the real world forces us to accept this or that theory as real. That's purely a matter of expedience of what we consider the best theory. And how we judge the quality of a theory is actually something that he doesn't talk much about, but you can see from his work, right? He has a very clear view that it needs to be a precise mathematically formulated theory, and you know.
Because isn't that in conflict with the definition of reality we are?
I'll get to that. I'll get to that. You're quite right. You're quite right. Yeah. So, I think I've summarized enough. So, just as a last point of summary, right? We've seen two examples of this distinction between phenomenal and objective reality. One in these covariant structures in general relativity, which of course are nowadays a very important point in all of field theory, right? It's long transcended general relativity, right? Any field theory that we think about these days seriously is a gauge theory, right? And it's exactly this gauge freedom that we're talking about. And on the other hand, statistical states, and that of course becomes relevant for quantum theory, which I want to remind you, right, till the late 1920s was thought of as a new kind of statistical physics, right? Nobody thought really, even after the development of the Bohr model, very much about quantum theory as describing individual atoms or individual microscopic processes, because they were always seen as just phenomena that you could always only observe in bulk. So the whole older generation, especially Planck, Einstein, Ehrenfest, were always thinking of quantum physics as sort of a new way of doing statistical mechanics. And I want to point out one interesting difference between these two examples that I want to get back to later. There is a statistical state, obviously, is an incomplete description of the objective matters out there, right? We don't know the exact microstate. All we know is the description in some bulk terms, right? And so a statistical state is always an incomplete description that fits lots and lots of different possible microstates. And that's, of course, exactly the important point about the statistics. On the other hand, these covariant states, right, in gauge theories, are not incomplete descriptions. They're actually more than complete, because they contain almost not just the information about the objective facts, but also a specific choice of gauge, of coordinates, of, let's say, the relation between the observer and the object. So, right, what we struggle with, for example, in general relativity, that's one of the main things that makes general relativity hard to work with, right, is that our states are always way more complex than the objective facts are, and but we cannot work without this conceptual fluff, right? All the sort of good mathematical theories we have these gauge freedoms in them. In both cases, right, we have not a one-to-one relation between our description and the state, right? But the reason why it's not one-to-one is exactly the opposite. So, chapter 2. Now we are turning to Erwin Schrödinger and his notion of Anschaulichkeit. Right? Another idea that from the 20s on was considered this old-fashioned, obsolete view of how physical theories should be, that Mr. Schrödinger stuck to and made him not understand the developments of quantum mechanics. So one famous letter he wrote to Bohr in 1926, right? That was right after the first debates between wave mechanics and matrix mechanics over the merits of each theory. Schrödinger gets invited by Bohr to Copenhagen, and Bohr bombards him with reasons why his preferred view of wave mechanics, namely as a theory of physical waves in space and time, cannot work, right? And so after this visit that Schrödinger gets badly sick at and comes home totally disheartened, he writes to Bohr, even if 100 attempts fail, one must not give up hope to succeed. I do not say through classical pictures, but through logically consistent representations of the real constitution of the spatio-temporal course of events. So what Bohr, of course, is developing exactly at this time is the view of complementarity, right? That we cannot have a consistent, unique description of microscopic events. Sometimes we have to use the wave picture, sometimes we have to use the particle picture, but both are complementary and both don't fit. But we have to live with this fundamental, what he calls irrationality of nature, right? We cannot hope to have sort of this one consistent theoretical model for microphysics. We always have to operate with these two opposing pictures. And so what Schrödinger protests is not the fact, he just says, it's not that I necessarily want this wave picture of classical field theory back, but I do want some picture. I do want one consistent model that explains me how quantum mechanics works. And the fundamental point, therefore, right, is this German concept of Anschaulichkeit, right? That's a little bit hard to translate into English, right? It means, Anschaulichkeit means basically visualizability, right? But it also has this more general meaning of intuitive, being able to be intuitively grasped, right? Being intellectually accessible. So Schrödinger, demand for Anschaulichkeit means that to be able to handle a theory, to understand a theory, you need a clear, concise, and precise model at its base that tells you what are the elements here, how do they interact with each other, what is sort of the ontological basis of that theory. And that's what he misses in Bohr's interpretation. That's what he misses in Heisenberg's uncertainty relation. That is what his fundamental protest against quantum mechanics in this modern form is. And so his big point of reference is Boltzmann, of course, and his idea of statistical physics, right, as a theory that is based on precise models, right? You build a specific model of a physical situation. You then do the statistical, its statistics, and arrive at macroscopic predictions. If they're correct, then you're lucky. If not, then you build a different model, right? The idea is not so much that the model has to be the real in the sense of like, that's what really how atoms behave, but the model has to give you exact predictions that then you can test and see whether they're successful or not. It's very similar to what Einstein said about the distinction between constructive theories and theories of principle. I don't want to go into the details here, right? Einstein thinks that a constructive theory, a theory that starts from a clear ontological model and then can build all kinds of situations out of these models, is superior in application than a theory of principle that just starts on general principles, like, for example, thermodynamics, right? You have first, second, third law of thermodynamics, and then have to see how you creatively apply those to specific situations without really having a model underneath. Let me make a short detour before I turn how this plays out with Schrödinger and quantum mechanics about how Schrödinger got to wave mechanics. And there you'll also already see how this Anschaulichkeit, this idea of intuitiveness, plays in. So quick look back, right? One of interesting question in the old quantum theory was how to explain Nernst's law, the third law of thermodynamics, right? That roughly said entropy approaches a constant at absolute zero. You cannot explain that in classical physics, right? From classical physics, you would always expect that entropy keeps going down, 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 and approaches, does not approach a fixed value. And so it was quite clear that that should have something to do with quantum theory. But nobody really was able to formulate a quantum theory of the ideal gas, simply because the old quantum theory was only a theory for periodic systems, right? You could like describe electrons rotating in atoms, you could describe vibrations of molecules, but you could not describe the linear motion of a gas molecule because there was nothing to quantize, right? All you could quantize with this old quantum theory, quantum conditions, were periodic processes. And so Schrödinger actually wrote several papers on this topic where he sort of ad hoc tries to invent quantization procedures, but nothing works, and he's sort of grasping in a fog. When, in 1924, something totally seemingly different happens, namely that Bose, a young Indian physicist, Satyendranath Bose, sends Einstein a derivation of the Planck law, so of the radiation law, that does not depend on classical electrodynamics. That was insofar an interesting progress, because that was always a weird paradox in Planck's derivation of the Planck law, that he had to use classical electrodynamics to describe the interaction between the radiating bodies and the electromagnetic radiation. And on the other hand, he had to totally reject classical mechanics for the idea of the quantization of the energy. So there seemed to be an inner conflict there. So Bose thought he had resolved this conflict by doing simple statistics of light quanta and simply counting light quanta as in classical statistical mechanics of the ideal gas. But, well, let me get to the but in a second. So Einstein picks up that idea, publishes his paper, Bose's paper, that had not been accepted for publication before, and shows that this is actually also a very interesting theory of the ideal gas, because it not only gives you this correct approach to constant entropy at temperature 0, but it also gives you a dual fluctuation term, which was a typical effect of the Planck law for radiation, and which could be seen as sort of showing that radiation was a strange mixture of particles and waves, right? This fluctuation term contained a term that was typical for fluctuation of particles moving freely, and a term that was typical for waves fluctuating. Bit complicated, I'm not going to go into that. But that fascinated Einstein because it exactly showed this strange behavior of radiation that sometimes seemed to appear like in particle nature and sometimes seemed to appear in wave nature. So Einstein says, here we have this new derivation of the Planck law that on one hand seems to give us a good new way of understanding the laws of radiation, but on the other hand can also apply to the ideal gas and there explain the Nernst law. But the interesting thing is that also implies that for the ideal gas, if that is correct, there should be the same ambiguity between particle and wave nature that there is for light quanta and radiation. And he refers in his second publication to another young physicist's publication that he had just gotten, namely Louis de Broglie's idea of matter waves. So he says there is an idea that matter really also can have a wave nature or this ambiguous nature just as radiation has, and that could explain a quantum theory of matter. When Schrödinger gets these, reads this article of Einstein, he first protests. He points out, right, he has done a lot of statistical mechanics, that there is a simple mistake in the statistics there, that what Bose and Einstein are doing is counting states the wrong way, right? you probably know that, right? That's exactly the salient point about Bose-Einstein statistics. You count states differently, right? Because you treat particles as indistinguishable, right? So you count states not the same way as you would count states of distinguishable particles. And so Einstein says, yes, correct, it's a different statistics, but it's successful. So there should be something to it, right? Should be something interesting about it. And so Schrödinger goes back and starts thinking about it and realizes if you see this statistics not as statistics of individual particles in different microstates, but as standing waves in a container in different states of excitation, then it makes perfect sense. Because of course waves are indistinguishable, right? So in a way, it's a very easy thing to see in hindsight, but it took Schrödinger a while, and it was this big aha effect for him that he realizes there's nothing unnatural about the counting of the microstates once you see that they're states of waves, right? Hence, de Broglie must be right? We must describe matter by a wave equation. And that, within a few months, really gets him to all his famous papers on wave mechanics, right? He publishes his paper on Einstein's gas statistics at the end of 1925. And in January of 26, he already publishes his first paper on wave mechanics. So he has, in this paper on Einstein gas statistics, he has this wonderful quote. That means nothing else, right? This discovery about, that Bose-Einstein statistics is really a statistics of counting waves. That means nothing else than taking seriously the de Broglie-Einstein undulation theory of the moving corpuscle, according to which it is nothing more than a kind of foam crest on a wave radiation forming the substratum of the world. It's very poetic. And it's, of course, also quite different from how de Broglie thought about it, because de Broglie explicitly thought about particles moving together with waves, right? He thought about two things there. There is the matter particle and a wave moving along with it, whereas Schrödinger is immediately convinced from the statistics, all you have here, all there is to count in the statistics is waves. So the particles disappear completely from the picture. And that's exactly then how, in his explanation of the Bohr energy values of the hydrogen atom, he explains the energy values, right? You don't need any particles and any orbits. All you need is to solve the equations of the standing waves of this electron wave in the hydrogen atom. So what he very much stresses, and as you know, this comes right after Heisenberg had published his first paper on what was to become matrix mechanics, which is a paper that's really deeply puzzling and very hard to understand. And besides Heisenberg and Born, sort of nobody really knew what to make out of it. And Born then quickly formulated sort of the mathematical content and introduced the notion of matrices, and it became known as matrix mechanics. But it was intuitively, of course, completely unclear what these matrices were about. Right. They were purely a description of observational terms, namely of the transition frequencies of different atomic levels, and it was absolutely not clear what that said about the atoms themselves. And so Schrödinger immediately stresses that unlike the Heisenberg-Born theory, his theory gives you a concrete physical model of how the atom works. Right? And as such, it's anschaulich, right? It's intuitive. And this does not just mean that it's nicer, easier to understand, but also, and that's something that he stresses very strongly now, that if you want to find new applications of a theory, you need to build these models, right? You cannot just work with some matrices in your head and think of, apply those to physical situations. And one example that he brings, and that actually was a problem for matrix mechanics, how do we, for example, treat the scattering of light quantum of an atom, right? The simple phenomenon of dispersion, right? We have a particle coming in, being scattered by an atom, and sometimes the atom absorbs some energy, and sometimes it doesn't. This whole theory of dispersion was, of course, a prime application of quantum physics, and but it was totally unclear how you could describe such a thing in matrix mechanics. Partly also, again, because matrix mechanics so far only apply to periodic phenomena, just like the old quantum theories. So Schrödinger seems to have an important point there, but quickly after, Max Born tackles this topic and actually does use wave mechanics. Because in wave mechanics, he can build a model and he can formulate a sort of theoretical base for the calculation, but he uses wave mechanics in a way that Schrödinger doesn't like at all, right? Because then, of course, what you get from wave mechanics is that you have a wave going in, hitting the atom, and then a wave going out. You don't get scattering events in any specific direction, and so you don't get any particle picture about what you would see when, for example, an electron gets scattered off an atom and hits a screen somewhere. So Born says we can only understand this outgoing wave from the scattering as a statistical prediction in which direction the particle will go. So these waves themselves are nothing but probability distributions for the actual course of events. This is, of course, what you know, the Born probability interpretation of the wave function. That's now absolutely standard, but that was exactly not what Schrödinger had wanted from his wave mechanics, right? He wanted these waves to be actual physical entities. And he immediately writes to Born and protests against this abuse of his beautiful theory, and immediately brings up the problem that Born uses now his waves in two completely different ways. On one hand, as dynamical objects, right, moving around, following field equations, and in the other hand, as statistical states describing probability distributions of particles. And he says you cannot have both, right? Either you describe the scattering as the scattering of a particle from a core and going in a certain way, or you describe the scattering of a wave, right? But then you need to take the wave seriously because it scatters differently than a particle. So doing both between is simply a logical mistake. And so Schrödinger tries to address this, what he now calls Göttinger Schweinerei, right? The obscenity from Göttingen, right? Schweinerei is the German word Schwein, which means pig. So he wants to try and show this Göttinger Schweinerei to be wrong. Here is the original quote from his notebooks. It says, averaging over the phases has to completely replace the statistical obscenity from Göttingen. This is in shorthand, in Old Austrian shorthand, which is a problem with deciphering Schrödinger's notebooks. So he tries to explain now this seemingly statistical behavior in these scattering experiments as interference effects of waves. And he spends a considerable amount of time, and that's really only seen from these notebooks of Schrödinger, trying to get ahead, reconstructing now what these people in Göttingen say about the statistical meaning of quantum mechanics as really an effect of interference of waves. And unfortunately does not get very far. But one thing he does happen, and that actually turns out to be a central problem, is that he realizes, right, because one case that he treats in great detail is the resonance between two oscillators, right? And Heisenberg had shown that when you look at the quantum mechanical state of these two oscillators in resonance, the only way you can explain their energy spectrum is by assuming quantum jumps, right? That energy packets jump between the oscillators. The oscillators are always in discrete levels of energy. And so the energy does not move continuously between these two oscillators, but it jumps. And so Schrödinger tries to disprove that. And as he treats these states of two oscillators in wave mechanics, he realizes, and that's again a quote, the joint oscillating states that appear immediately with the interaction are of such a kind that they cannot be dissolved into states of the single system.
And what's this?
This was, as these notebooks are of course not dated, so it's not quite clear, but it must be sort of later in 1926. You know, in the connection in these discussions with Born and Heisenberg, so summer, fall of 1926. Worse, it seems even if one applies the interaction slowly and stops it again, the remaining oscillating state will be of the above-mentioned irresolvable kind. So, in hindsight, right, what we see here is that this is the problem of entanglement, right? He has two systems interact, and what he gets with is of an irresolvable kind, right? A state that cannot be explained as two independently existing states of the two particles, but of some weird mush-up of the waves. And he does not call it Verschränkung yet here, but he spends quite a bit on, you know, two big notebooks on like trying to deal with these states and trying to understand what's going on there. So obviously, right, I mean, the phenomenon of Verschränkung he's already discovered in 1926. He does not publish about it, right? It's an embarrassment to him because it really shows him that his original idea of treating these matter waves as physical waves does not work, right? They're irreducible in high-dimensional phase space, right? Two particles, the matter wave is in 6-dimensional space, and there is no way of like reducing these to waves in 3-dimensional space. So his main argument that, you know, matter waves give you this intuitive physical model of what's going on in microphysics is failing. So he tries into the 1927, and in 1927 is the Solvay conference, and he still defends this view, but soon after he finally gives up and resigns this idea, and sort of ends now looking at quantum field theory as a possible answer to these problems. Because that's sort of his conclusion he takes, right? Quantum mechanics in this form, in the 1925, 1926 form, is a non-relativistic theory, and so it's not really correct anyhow, so we need to see what's coming in the future, and so that he gives up on quantum mechanics. So let's turn to the EPR paper. Einstein sort of has followed these events as an outsider, right? He's originally quite excited about Schrödinger's wave mechanics, but he also quickly realizes that there is a problem with this, right? That it's not a theory of waves, of physical waves. And so he sort of his enchantment with wave mechanics wanes, and he sees quantum mechanics just sort of as a continuation of this statistical theory of atomic orbits that gives you sort of a good statistical description of what's happening, but it doesn't really explain you what's happening really at the level of the atoms. And he turns to unified field theory, right? His idea of extending general relativity to a more general theory encompassing electrodynamics as his best hope to explain what's going on in microphysics. So Einstein only really treats quantum mechanics from this critical point of view. He especially protests this Heisenberg idea of the uncertainty relations, and his basic point of argument is, right, quantum mechanics works well as a statistical theory, but it is just that, right? It's just a macro description of a hitherto unknown microphysical processes that we really want to understand. So his main complaint is, right, that the Copenhagen School, or what's later gotten called the Copenhagen School, right, everybody around Bohr, Heisenberg, Born, treats these statistical states as an objective reality, right, as something that's really out there and can have a physical equation of motion, right. The Schrödinger equation is a classical equation of motion, right, and in his view, just as in Schrödinger's view, as I said before, right, that's just a contradiction, right, to say that a statistical description of events could have a deterministic equation of motion. How did he get now to the Einstein-Podolsky-Rosen paper? There was always somewhat of a mystery how he suddenly in 1935 came up with this paper. One thing that Don Howard pointed out early on is that it seems to be related to a thought experiment that he published with Tolman and Podolsky in 1930, where a photon escapes from a box, and you have the choice after the photon escapes to either measure the time of escape of the photon or the energy of the photon, right? And so there is a certain relation there that you have this free choice of what you measure, just like in EPR, but you're of course only talking in a very indirect way of an entangled state insofar as the big state of the box and the state of the photon is entangled, but that doesn't really yet get any theoretical expression. And so how exactly this then developed into the EPR paper was rather unclear till we found in Schrödinger's notebooks two big convolutes where there was all kind of stuff in, but some manuscripts that Schrödinger called Szilard-Spiegelmessung, so Szillard's measurement of the mirror. And there is a short paper that begins. This concerns a question raised by Szilard at the colloquium yesterday, dated November 5, crossed out, 4th, 1931. So it's about a question that Leo Szilard brought up after Einstein's colloquium, which we know was on the 4th of November, 1931. This is where he presented this mirror box experiment. And the situation that Szilard brings up, that Schrödinger draws down in his notebook, is that a light quantum gets reflected from a heavy mirror, right? I'll read you Schrödinger's description in a moment. And this is, so this is how he draws it in his notebook. And as we then only afterwards realized, I just talked to Marcus about that he actually already had seen that letter and understood that letter before we ever stumbled over it, in a letter of Sommerfeld that he writes a week later. So at first, Schrödinger is rather scandalized by that idea because Szilard claims that with this setup, you can, sorry, picture back, measure either the momentum or the position of that light quantum with any precision that you want, right? Sort of subverting the Heisenberg uncertainty relations. So he has first spent some time to try and refute this conclusion. But in the term of trying to refute Szilard, he actually writes down exactly or pretty nearly the wave equation that then Einstein-Podolsky-Rosen used in 1935. So we see this very nicely in this letter that Schrödinger writes to Sommerfeld a week later, where he's actually already come to realize that there is an interesting question there. He writes, "The foundational problem torments me more and more, unfortunately quite unfruitfully. In the seminar, we have discussed the following, actually quite simple case for ours, right? You have a mirror that the light quantum reflects on. Initially, we very accurately measure the momentum, namely 0 of the heavy mirror, and the position of the light quantum. Then let the photon reflect on the mirror. After the photon has separated some distance from the mirror, we have the choice by a measurement on the mirror to determine either the position or the color of the photon. Because the photon has nothing to do with the manipulations on the mirror, one can hardly say that its sharp position or sharp momentum is only created by one of these manipulations. In any case, this is not a creation in a real, but at best in a mental sense. One would like to conclude that the photon always possesses a definite position and momentum, a view that we have long ago abandoned as paradoxical." Right? So this is exactly, of course, the setup of the Einstein-Podolsky-Rosen thought experiment, and it exactly already gives you that conflict, right? If we think of this distant photon as having an independent objectively existing state, right, then we really have a problem to understand what's happening there on the other side when we measure the mirror. So somehow, right, still not quite clear how, but somehow, right, Podolsky and Einstein got this too. And as Schrödinger writes later, right, there has been long discussions of this example. So this was obviously something that they talked about. And in 1935, they published the famous EPR paper. And Schrödinger immediately writes to Einstein and congratulates him on the paper and says that, yeah, this problem was discussed for hours back in Berlin. And immediately writes Einstein a very detailed account of how this is to be treated if you don't have a perfectly entangled state, if you don't have maximally entangled state. So it's clear that he already has done all this at some point before. And very soon after, right, he writes this 3-part paper where he takes his stance on the EPR situation and analyzes this from his point of view. Einstein's response is, first of all, to complain about the EPR paper, right? Pretty much the first thing he said is that the main issue is, so to speak, buried under learnedness. And then he gives Schrödinger a short account of what he wants to say, and that is way simpler than the original paper. And actually then Einstein only years later in 1948 publishes as a separate paper in Dialectica in a special volume in honor of Wolfgang Pauli that is the argument I will give you in a second, right? It comes down to quite a different argument than what's published in the original paper. So Einstein's presentation to Schrödinger goes that way, right? You also somehow prepare a pair of particles in an entangled state. They're separated sufficiently. You perform a measurement on some observable, whatever you want, on the first particle. And then, you know, whatever that observation was, whatever the observable was, you have a definite state of the second particle. And now you perform a different measurement on the different observable, and again ascribe a definite state with a different value of that observable to the other particle. So whatever you do, you want to say, right, the particle on the other side, if I believe in locality, nothing should have happened to it. It should always be in the same objective state, right? Nothing over there should change by my measurements here. But I have now two different state descriptions depending on what I do on my side, which measurement I prefer. So the same objective reality over there of that particle has two different descriptions. And that, again, shows, right, the relation between the objective reality of what's out happening on the other side, on the particle, is not a one-to-one relation with my descriptions that I give of the particle. And hence, from this follows, right, that quantum mechanics cannot be the last word. It's only an incomplete description of what's going on, which is, of course, the conclusion that Einstein wants to get to. Yeah?
I'm just curious, in this story that we heard in various ways, was it considered the possibility that it's wrong to demand a one-to-one relation between your description in terms of the physical theory and reality?
That's, of course, the question, right? Einstein here takes it simply as an indication for the fact that we're talking about a statistical state, right?
That's a criticism of theory, but you can take it as an input.
Pardon me?
It takes it as a criticism of quantum mechanics, but you can take it as an input to demand that.
Sure, you can. You can. But that is sort of the observation that Einstein takes as given, right? And this is probably, right, I mean, it is not a very convincing argument if you don't share Einstein's conviction that, you know, this is an indication of a statistical state that you don't have this one-to-one description. And that is probably why Podolsky insisted on this learnedness of the EPR paper, this criterion of reality that is introduced that actually goes further, right? In the EPR paper, you have now additionally this criterion of reality that lets you conclude from the fact that you have ascribed this state to the particle on the other side to an element of reality that has to be there, right? And hence, right, we have a stronger conclusion than in what Schrödinger writes to, what Einstein writes to Schrödinger. So you're totally right, right? But this is sort of Einstein's simplified way of talking. Did you want to say something?
I often had one impression. I mean, how about the following position? Einstein was correct in saying that the quantum mechanical description is incomplete. But that does not mean that it is completable.
That's the question, of course, yeah. Right? No, that is the question.
And I don't think did he ever claim later on that it has to be completable, except in the last sentence of the EPR paper?
Well, that was, of course, his whole program of unified field theory, right? I mean, his whole program of unified field theory was this idea that you find a more fundamental, deeper description to which quantum mechanics than just the sort of the statistical level above, right? So this whole idea was that, you know, there's more to be found, right? Quantum mechanics is only a first step. And so I would say yes. I mean, he hasn't vocalized it quite explicitly, but, you know. But that's in behind all these, you know, remarks like God doesn't play dice or so.
Quite completable, do you mean not possible for people to complete it eventually, or not inherently completable as an objective reality?
That is, of course, also a question, right? I mean, you know, Bohr and Heisenberg would have said not completable in principle, right? It is objectively so that these states have this dispersion that can never be resolved, and, you know, any attempt is misguided. Although, you know, with Bohr you can always read it this way or that way, so I'm not quite sure if some other intelligence, right, some non-human intelligence might be able to, but we are not in any case. Right? What I want to point out again is, you know, what the gentleman already says, right? The conclusion that this shows that quantum mechanical states just are statistical states does not really follow from the argument, right? All Einstein has shown is that there is a not one-to-one relation, right? So everything else is just sort of his interpretation of statistical states are states that don't have a non-one-to-one relation with objective reality. And this additional argument in EPR is weird and unwieldy. And what I also want to add is it exactly conflicts with this earlier view of Einstein that I stressed so much, right? This neat separation of phenomenal and objective reality, because what this criterion of reality tries to do is try to deduce directly from the appearances, from what we can predict and observe, to a theoretical concept of objective reality. So it exactly conflicts with this neat separation of concepts that Einstein proposed to Schlick. And Schrödinger also immediately protests, right? He likes Einstein's argument, but he doesn't like the conclusion. Because, first of all, he says there is no such model. And he also argues, and that comes to your question again, there cannot be such a model because he brings various kinds of no hidden variable arguments, right? You've heard of these arguments, why it cannot be, that also Heisenberg then brought in the consequence, why it cannot be that, you know, just by addition of more information, you can explain quantum correlations simply from these underlying variables. And Einstein just swipes this away, says, I don't quite understand your argument, and anyhow, I'm not saying that it has to be exact, right? It could be approximate, and so he is not easily discouraged. But then, of course, the rest of the story I don't need to tell you. I'm sure you all know this very well, right? Comes Bell, brings his inequalities that actually give you a measurable way to test the predictions of Einstein's idea of separable locally defined states. And as we now know, thanks to a lot of wonderful experimental work, that's been confirmed wonderfully, right? Quantum mechanics is right, and this kind of a local theory of local states cannot explain the quantum mechanical correlations. So Einstein's simple conclusion, yeah, this is just a statistical state, obviously doesn't work. But what I do think is that this distinction that he made originally between objective and phenomenal reality is actually a great idea, and that helps us actually in also the interpretation of EPR. And so that's what I want to quickly now breeze through because I'm running out of time. A little philosophical epilogue on how to view EPR under this distinction of Einstein of objective and phenomenal reality, and how this recovers a lot of the demands of Schrödinger for intuitiveness. So basically, right, EPR, or the falsification of EPR's prediction, leaves us with three possibilities. We can sort of become positivists and abandon this idea of constructing an objective reality in this Einsteinian sense, right, of this, like, you know, a precise theory of objective facts. We have to remain, as you said, with these incompletable states that don't give you a precise description of what's going out there. And only once we observe things do they become describable. We can keep demanding what Einstein demanded and what Einstein and Schrödinger demanded and say, but we want such a theory, and we need to modify quantum mechanics in such a way that it fits that. And you know, there's been all kinds of attempts of doing that, right? Physical collapse theories like Girardi-Rimini-Weber, nonlinear quantum mechanics, hidden variable theories, right? The original idea of de Broglie that then Bohm developed of, like, you know, there is particles that carry these hidden variables underneath. But then, of course, and that follows from EPR directly, right? We do have to accept that we have explicit, non-local processes that transport the information of the measurement to the other side of the system, right? We cannot have one without the other. And that I still find, and I mean, it seems to me now that nowadays it's become, at least in philosophical circles, quite standard to take that as the lesson of EPR and the Bell inequalities. Yes, the world is non-local, right? We have to accept that there is these non-local processes in observations of entangled systems. And I must say, I don't like that idea at all. Not only because it is locality in all of the rest of physics is still this absolutely fundamental concept, right? I mean, the whole idea of a field theory, including quantum field theories, is based on the notion of locality, right? That all your actions are purely local. But even more, I find strikingly, is that quantum mechanics itself says that nothing observable happens non-locally, right? That's the null signaling theorem, right? What happens ever when you observe an entanglement can never serve to transport information from one side to the other. So you have to believe in this weird conspiracy that you have these local interactions going on, but nature covering up all its traces so that on the phenomenal side of the story, it looks like everything is happening locally. And these kinds of theories are usually not very successful in my historical experience. Or, and there's a third way out, you go back to this second case of Einstein's example of a non-one-to-one description and think, what if we accept the description of quantum mechanics to the objective reality is not one-to-one, but not because it's a statistical state, but because it's a gauge state. Because it's an overcomplete state, it has too much information about objective facts. So how does that work? I'm again too fast here. This is nothing but Everett's interpretation, right? What Everett says, am I now too far? Yeah, here, sorry. What Everett says is the entangled state does not get destroyed in any way upon observation. The only thing that happens is that the observer on the one side interacts with a particle on the one side. So he or she becomes part of the entangled state. We have a big entangled state involving observer, particle on one side, particle on the other side. And it's that entangled state that carries the correlation. Because what the entangled state describes is a statistical multitude, but now not in the sense of a statistical state, but you have to accept in the sense of a real existing ensemble of possible states, in which of various observer states having made various observations, but the entangled state guarantees that each of these observer states is correlated with the state of the particle on the other side. So it's no surprise that then when we close the circle and observe the particle on the other side, we find the exact correlation that EPR demands, but nothing non-local has ever happened, right? The only thing that has physically happened is the interaction between the observer and the particle on her side that establishes the entanglement, right? So we have locality, we have a correct description of phenomenal reality if you believe Everett's claim that we can sort of, without contradictions, understand a quantum mechanical state as describing an actual ensemble, not a statistical ensemble. And we have still now, perfectly mechanical description of the goings-ons on the micro level, which does not leave a lacuna like in the Bohr way, where we simply cannot say what's going on in the moment of a measurement. Right? So to transport that back on my earlier distinction, right? The measurement outcomes are only part of the phenomenal reality, right? They are this, what we see directly in our experiments, but they're not elements of the objective reality of this theoretical construct of what's really happening. The objective reality is always described by this huge entangled state of everything, right? What Everett calls the universal wave function. So, and this universal wave function describes not one single phenomenal reality, but a gigantic ensemble of possible realities. Right? And so that's what I see as the theoretical core of the Everett interpretation, and why I do think it is an attractive way of thinking in Everett's way about quantum mechanics, because it doesn't force us to assume mysterious, actions at a distance, and it does give us the hope that we actually can construct some sense of objective reality. Let's go through this. One thing I want to just point out as my last word here, most people, when they hear Everett, immediately get into a slight sense of panic about this moniker of many worlds, right? This idea that, what Everett posits here is some like insane metaphysics that is in no way for us acceptable as a rational way of thinking, especially philosophers tend to that. I think the metaphysical attitude you have towards Everett is not in any way predetermined, right? You do not have to say that this objective reality of the entangled state is what the world out there really has to be, right? You can say, like, for example, Osiander said about Copernicus's world system, right? It's just a practical way of calculating. We do not have to believe that the Earth actually rotates around in the universe around the sun. We just can calculate that way. Or you can simply say, right, that what physics can only give us is a sense of all the possibilities of events. It just cannot give us a concept of reality in our standard philosophical sense, right? In a way that is no different than in classical physics, right? Physics only gives us equations of motions. It does not give us boundary conditions. It does not tell us what time it is now. It does not tell us, where particles are when, right? And so you might as well say that physics also doesn't tell us that this is our reality and no other one, right? It just gives us a big range of possibilities, and we have to leave the decision of what's real to our phenomenal reality of that what we directly observe. So this just as sort of a little word about why I still think that Everett's I wouldn't even say it's an interpretation of quantum mechanics. It's just a further development of quantum mechanics that lets you then use quantum mechanics in ways that I would consider much more rational than the other interpretations do. Because if you believe in the hidden variable theory, right, you should actually look for these effects of these hidden variable states, right? That's what Bohm originally thought, right? That there would be interesting physics there, that we find these particles behind the quantum mechanical states and how they deviate from them. Nothing came of that idea, right? Same with collapse theories, right? Now we need to search for, where exactly do quantum mechanical collapses occur spontaneously, right? How big does a mass accumulation have to be so its state collapses into a microstate? Also, that hasn't gotten us very far. So I think what's nice about Everett is there's only one process between the micro world and the macro world, and that's decoherence, right? That's all you need to explain the difference between our macroscopic appearances and the realm of quantum mechanics. And everything else is sort of taken care of by this idea of the quantum states as actual ensembles. So if you swallow that, you don't have a lot of other worries. And that's what I want to end on. And that's what I, that's my final point here, that in a way, this is the only way to follow this Einstein and Schrödinger idea of a theory that should have a clear ontological base and should have a clear idea of the distinction of objective and phenomenal reality. Because, of course, that's another thing that gets totally mixed up in the Copenhagen interpretation, in the Bohrian idea that it's only our direct observations that create objective reality out there. So insofar, right, and Everett himself considered himself a good Einsteinian. He says that in the introduction to his dissertation, actually. Okay, enough. Thank you.
Thank you very much, Christoph. Should we continue the questions?
I just had a quick question about the end. So, are you kind of saying kind of developing like a structural realist understanding of the way you function? Like, they don't describe like actual ontology like things, but more like structural relations about possibility in the same sense of the equation.
Well, in a way, right, I mean, structural realism is again an answer to the old epistemological philosophical question of reality. What I'm saying is that this, this entheorized distinction of Einstein of objective reality and phenomenal reality has nothing to do with that. We should find a different concept here. We shouldn't call it both with the same name, because what Einstein talks about is not epistemology, it's methodology of science, right? It's that within science we construct this notion of objective reality that does not need to have any ontological or epistemological weight, right? We're not claiming that these theoretical entities have to in any way resemble what we observe, right? What we observe is the simple basis of our theories, but otherwise our theories, and that's Einstein keeps saying that, especially in the 20s, free creations of the human mind, right? We can make up any story about the world as long as it works. And so structural realism is, again, a much stronger claim, right, that there is some similarity here to something. But the question is always to what? What is that it should be similar to, right? Certainly not our direct appearances, right? Not that what we see in front of our nose, right? Physics has long gone beyond that. So I don't think it has anything to do with this idea. No?
So thank you. It was a very nice presentation. I want to ask you something, especially a bit on the last slide you have, where you somehow put a different criterion, which was not about whether it's one-to-one correspondent to objective reality, not about whether the description is redundant or not,
Maybe I should not close it.
Theory leads us to good questions. And I'm guessing that you are taking this to be as an argument for the Everettian way.
Yeah, but that is a meta-theoretical argument, right? Again, that is not the same level of asking than the distinction between phenomenal and objective reality.
That's the answer to my question. The question was whether you take this, I actually agree with this statement, but whether you take this to imply this nice feature that the Everettian theory is closer to reality.
No, that's the thing, right? I imply this to say that the Everettian theory is more useful, right? It's perfect. It's basically that it's just a sort of Machian utility argument, right? The best theory is the theory that's the most useful. So it has nothing to do with any realism in the sense of, structural realism or, realism. And that's what I explicitly want to say about, interpreting then, this whole many worlds talk, right? This is not how we have to, that is an interpretation of Everett that Everett himself never proposed, right? I mean, that was never, Everett never talked about many worlds. That was Miesner that invented that term. So the idea of many worlds as a explanation of what's going on there, you can take or you can leave. I'm just trying to go back, but was that it? Yeah. So the question of theory choice, I think, should be completely independent of questions of reality, right? And that's why I, don't like a lot of contemporary philosophy of science, because they're still always entangled in these questions of, trying to find a criterion of theory choice that somehow transcends physics, right? Somehow philosophers can tell the scientists how they should choose their theories. And I think that's just misguided. It's never worked before, and I don't think what we should expect it to work.
That's very clear for me. Thank you. I actually agree with you. So I wanted to say something about many words, although you were very careful of saying that's an interpretation of Tolkien. Just curious if you would agree with it. So let me take the many words interpretation, because I haven't worked in this, I'm not a specialist, but I admit that I use it all the time.
Oh, actually, sorry, we are supposed to use the microphone, right? Herr Zeremoniendirektor.
So I actually use the way the visualization that many words gives you all the time, I think many. For me, that makes it a good interpretation because it helps me think. But what I would suggest is a good interpretation in this sense that helps you visualize things, like there was requesting, should be taken by the fact that it's a good interpretation, it helps you visualize things, to imply that it is further from whatever it is you want to call reality.
That it's further?
Further from whatever it is that you would like to call reality. Because what I find surprising with these huge giants at the time is to somehow imply that whatever would be intuitively satisfying to us would be closer to true reality. But that would be very surprising, right? Because we're just some random descendants of apes.
No, but that's, I think, exactly what Schrödinger wants to deny when he writes to Bohr, right? He does not look for, he does not hope for like recovering sort of classical physics in that sense. He just wants some precise notion of what's going on. Whether that describes what's really going on the level of atoms or not doesn't matter, right? What matters is that it's applicable and that it's useful. So the question, if that then really describes a metaphysical reality out there, is not of his concern, right?
I see. I'm suggesting something a little bit more radical, to say that whatever is more useful for us should be further away from whatever it is you want for reality.
No, not further away. It's just, what I want to say is that reality does not play really a role in there, because that reality that the philosophers like to talk about, we don't have any access to anyhow.
Does it work?
Yeah.
Work?
No, it's only supposed to work for the recording. It's not supposed to work for us.
Recording.
No, it's not recording. This is we're streaming it without recording. Just the online audience.
Yeah. Okay. Two small points. I think one, but we can talk that in person. If you make usefulness a criterion, then this is very thin ice, because we don't know what may be useful today might not be useful tomorrow. This is just a small comment. We can talk in person about that. I want to quote John Clauser, and I recommend everyone here to listen to his Nobel lecture. I think it was a fantastic piece. And he said there's an elephant in this room when we talk about entanglement and the reality and all this. The elephant to him is that quantum states do not live in real space. They live in configuration space. And if you realize that, then a lot of the discussion goes away. This is really very interesting. I have one question to you. What to you is the quantum state? I want to quote here, I am very much of a Copenhagenist for the reason because this is the most austere interpretation of quantum mechanics, which doesn't assume anything which is unnecessary in the Heisenberg sense. Heisenberg says, and this is really, really a great statement, the quantum state is just a representation of our knowledge, and so it's not out there.
Sure, you can say that.
And he says, when you do a measurement, you get new information, and what would be more natural than to update your representation of information with the quantum state? So there is no problem with collapse, there is no measurement problem with this.
Sure, you can of course say that, right? I mean, that's what I say. You can always return to positivism.
And what to you is the quantum state?
That's what I'm saying. The quantum state is sort of supposed to be a representation of objective reality, not in the sense of this metaphysical reality that Heisenberg thinks of, but of objective reality in the sense, for example, that it follows an equation of motion, right? Why should my mental state follow an equation of motion? Why should my beliefs develop independently in a lawful physical manner that we can very exactly, precisely calculate now to incredible detail? I just don't think, to me, it's always like a relatively easy excuse to say, well, this is just my description, and this is exactly what physics does, right? Is that out of our descriptions, it constructs something that it describes as independently existing. And it's no different than what we do in general relativity or in Newtonian physics or in electrodynamics, right? What we do when we work with wave functions is exactly the same. So to say just now in quantum mechanics, suddenly we fall back to saying this is just a representation of what's going on in my head, just doesn't sound very satisfying to me.
We should continue in person. I don't think that this viewpoint, which I just quoted, has nothing to do with my head and my mind.
Has nothing to do with your head and mind?
With my head and my mind. But we should continue in person.
You think that it doesn't have to do with your head and mind?
It has nothing to do with head and mind. It's a representation. It's a representation of knowledge, of information. But it's not happening in my mind. It's not something.
So the knowledge is, the information is something happening independently of you as an observer.
Exactly.
I mean, yeah, sure. But then, I mean, I want to have a clear theory of that theory of of that information.
We should talk.
Yeah, definitely. We still have a while to talk.
How long are you here now?
Pardon?
How long will you be here now?
Till end of next week. So I hope we'll have a chance.
Also for a final comment, so adding to that discussion, the letter that you quoted from Schrödinger to Sommerfeld, this is where I think, if I remember correctly, where Schrödinger says that the thing of quantum theory, that it's a radical departure from the ways we have so far used physics to describe nature.
Yeah. And that was, of course, sort of part of the protest, and that sort of, also was part of the credo now of this new generation, of the Heisenberg-Pauli-Jordan generation, that these old guys just didn't accept the fact that we now have to do physics completely differently than we did before. And of course, that is a perfectly possible viewpoint. Just that a lot of the justifications for this viewpoint of that this is that quantum physics needs a totally different way of thinking about physics have played out quite strangely in the last 100 years, because in a way, nowadays, we're using quantum mechanics very much exactly the way that we use that we have used other physical theories. There is nothing that different about our describing, in principle different, about our descriptions of atoms in terms of models than it was in the end of the 19th century when Kelvin constructed his vortices of ether, right? We do have these very nice and in many ways intuitive ideas about, you know, how atoms are built, how forces are working. So to at the same time still maintain that, you know, our use of quantum mechanics has to be radically different from everything that we've done so far in physics, to me sounds less and less plausible as time is going on. But that's my point.
I think this is a perfect statement for initiating more discussion. We'll have the time. In the next 10 days, I suggest that everyone here uses the time. I think, Christoph, you have an office also on the 4th floor?
4th floor, I think 410, if I remember right.
Next to Birgitta, so make use of the time that our visitors are here, and approach Christoph, grab him, and we will find some joint activities. Okay, super. Thank you so much.
Thank you. Das Interessante ist...
Ich muss leider laufen. Mein Problem ist,